Hello everyone. Here I'm going to solve 9 different problems related to module 2, axial or normal and shearing stress and strain. After seeing each problem, I suggest pause the video, try to solve it yourself, and then watch my solution and compare your solution with yourself. If you run into any problems which you couldn't follow my solution, please do not hesitate. Contact either me or my TA and we are happy to help. Let's get started. We start with problem 1. So let's see what it asks us. It says we have a rod and it is under a different axial load, 1 kilonewton here, 2 kilonewton and 3 kilonewton here, and it has been fixed to the wall to the left. We have a module of elasticity. It's made out of aluminum alloy. So the question asks us to find the total deformation of this rod. It's a classic problem, something that you need to know how to solve. So the first step, like always, we start with the free body diagram to find the reaction forces basically. So the reaction in this case is just one axial load from the wall, which is obvious because we don't have any other extra load. So let's call this one R, and from the equation that we learn, sum of the force in X must be 0. And remember, as I said during lecture, always we consider basically to the direction to the right as positive. We don't have to, but as a rule, let's say we consider that positive X always. So if I write down some of the forces in X equal to 0, then I'm gonna have R minus 3 plus 2 minus 1 equal to 0. Simply it gives me R equal to 2 and my unit is kilonewton. All right. So the second step, we decide for unit. So E is in gigapascal, module of elasticity. I suggest instead of gigapascal use megapascal. It's easier to work with. So E then is 69,000 megapascal. So when we say megapascal, it means Newton per millimeter squared. So we should know that all the length and anything related to the size, it has to convert to millimeter. And then we see what is the key formula to use here. The key formula delta is FLAE, the formation. We are interested in finding the formation. But we notice here we don't have only one force, or the A is changing, right? The cross section A, here the diameter is 20 millimeter and over here is 10 millimeters. When we are dealing with a scenario when we have different section, then this delta we have to break it down to different area, and we say delta is sum of different FLAE. But how we decide to break it to different area? So we start from the left side and we say, well, if let me put a boundary here. I start from the left and I say, as I move to the right, everything is the same until this point, right? At this point, we see there is a change. There is a load that has been applied. So I put another boundary then here. And then from this boundary, I move to the right, keep going, and then I see over here, all of a sudden there is a new load, and also, even if there is no load, the reaction change here. So I put the boundary there, And with the same concept, if we move to the right, everything is the same from this point. Everything is the same until the end, which we put another boundary there, right? That's the end. So what I did, in fact, I break down this rod to three basically region, right? Region 1, region 2, and region 3. Now I have to calculate this FLAE separately for each of them. So it's equal to then this relation F1, L1, A1. What about E? The material is the same for all of them, so I just leave it E. Plus F2, L2, A2, and E, and plus F3, L3, A3, and E. So even if the material was different, that was okay. Then you put just the E for each material in each section. Now our job is to find out this parameter for each basically region 1, 2, and 3. E is the same. We have the value. That's easy. A1, A2, and A3. That's also is very easy. We have the diameters. Let me write it down here. So A1 is equal to A2 is equal to pi r squared, which r is 10 millimeters. So that's also is easy. And what about A3? Let me write it down here. A3, region 3, the diameter is 10. So it's going to be then pi 5 squared. So we dealt with area. What about length? Each of these regions we have the length. Like region 1, the length is 25 centimeter. So then L1 is 250 millimeters. Let's do the conversion now before we forget. L2, the length of region 2 from this boundary to this boundary is, we can see 75 centimeter here, 25, so it gives me 500 millimeter. And L3, we can read it, it's 450 millimeter. So far good. We have area, we have module of elasticity, and we have L. So the only piece of information we need now is this F1, F2, and F3, right? And that's the key point in solving this problem. How much is the reaction in, or the internal load in region 1, right? So remember, we are looking to find F1, F2, F1, F2, and F3. And remember, they are internal loads, internal reactions. So I suggest, you may have a different solution, but I suggest this simple solution to find this F1, F2, and F3 correctly. And I suggest for other problem also you should maybe follow the same solution. First, we try to draw the basically the external load diagram. So let me show this one to you. This is, imagine this is X axis, and let's say this is the y-axis, but here the y-axis is the diagram of external loads. So let's call y external, to be exact, axial load or normal load, right? We just want to draw these loads, the diagram, how they change as we move toward right, which we call it X. So we already found R. We know R is equal to 2. So it's very simple. We start from basically origin, 0 here on this graph. And as we saw the numbers, we basically we draw them, right? So at the beginning I see a jump of 2 kilonewton, so it means my graph has the value of 2. So let's think that this is 2, all right? And then I don't have any loads, so everything means everything has to be constant. And then I have a jump of 3, and it is negative, right? If it is negative, so it's coming down 3 units. So it means this point now is, remember, this point now is minus 1. Because remember, we have to jump from this point 3 units. Because we had like 3 kilonewton, we have 3 kilonewton, and it is negative, it is to the left. So we keep going, everything is constant, so we go all the way here. But here all of a sudden we see there is a positive 2 kilonewton. It means I have to have a jump of 2 kilonewton, right? Which means I get to the point where it is plus 1, right? And then everything is constant to the end, right? And at the end, what we have minus 1, right? So it means I have to come down 1 unit. So one way to check that our solution was correct is at the end we have to return back to 0. Remember, we started 0 and we return back to 0. Because remember, it is a static, everything has to be balanced, and if things has to be balanced, so simply it means we have to return back to 0. It means sum of all these forces must be 0 at the end, right? So this diagram, we call it the external axial loads, basically. And one more time, simply you start from 0. From what you see a positive 2 here, you jump 2 units. Everything is constant, you go constant, no change. Then minus 3, you come down 3 units, and then everything is constant. Then from minus 1, you have a positive 2 here, so you jump 2 units, so it is 1. And then everything is constant all the way to the end, and then you jump down and you get to 0 point. All right? So, but keep in mind that we are looking for internal reactions, right? Internal reactions, not the external loads. The diagram that we just draw here is the external loads. So if I want to draw the external loads, I just solved it for this problem. Later you realize that you don't need to draw these second diagrams. This is just for the sake of discussion for this problem. Later you realize that there is no need for the second diagram, but let's do it correctly so we can understand each step. So similarly, this is X, but this time instead of external load, it is internal reactions. Right? Internal reactions. Let me write it better. Internal reactions. All right. So we said whenever we apply a load, the reaction is the same load with the same magnitude, but opposite direction. So using the same concept, it means whatever I see in this graph, the internal reaction is just a minus, multiplied by minus sign. Or in other words, we just need to flip the whole graph. So for example, if I start from 0, so I have to come down 2 units. This is plus 2, but this one is going to be minus 2. And yeah, whatever I see over there at the top, I just flip it, or I just multiply it by a minus sign. So if I multiply by minus sign, I get to this point. Then I come here. Now remember, this one is plus 1, right? We had minus 1 here. Now it is plus 1. and then this one we go down here to -1, and the rest, which is a constant line, and still we have to go back to 0, right? So pay attention, the internal loads then, or the internal reactions, is the negative sign of these external loads that we draw. So how this diagram now this is the key diagram that we want to use. Like, this is what we were looking after. But how this diagram can help us? Well, if we look at this diagram tells us that in region 1, if we look at region 1, your internal load is a constant load and it is -2. So from the graph, we can write down F1 is equal to -2, and let's do the units conversion as well, 2000 Newton. And similarly, what is F2? It is positive 1000 Newton. And what about F3? It is -1000 Newton. So we have all the information we need. We got the forces, we got the area and the length, and we have E with the correct units. If we substitute all these numbers in this formula delta, and don't forget with the correct sign, don't forget this minus sign, we will find delta deformation, which is minus 0.6227 millimeters, and I can round it up to maybe 3 significant significant figures after decimal points, 3 millimeters. So that's the total deformation of this rod, right? And this total deformation is negative. It means the whole thing's shrink. Although here you see we have a negative load here, but this 2 kilonewton is positive, but maybe because of this 3 kilonewton, things can shrink. And the sum of the whole this change in length is a negative numbers. All right. So let's move on to the next problem. Problem 2. First, let's understand what it is exactly. So here we have a link AB, and which is connected by a cable to the ground. So this is cable BC. The question says it's a cable, so it's not a rod, it's a cable, and we know its diameter. Also, we know it's made out of steel, and we have its module of elasticity. So this is the information that we have, and it has been joined to point A. So we can imagine if you apply load P here, you want to rotate this link AB to the left, or in other words, you want to rotate it counterclockwise, right? But there is this cable that prevents it from rotation. In other words, when you apply load P here, so there will be a tension in the cable. Let's call this tension T, which prevents it from falling to the left and rotating, right? So this is the cable. Let's call the tension in the cable T. So let's see what the question wants us to calculate. The question says that find the maximum load P, like this load P, so that the stress in cable BC does not exceed 180 megapascal, right? So that's we want the stress must not exceed 180 megapascal in this cable. Also, there is another condition. We know when there is a stress, it's going to be also extension or elongation in the cable, and we don't want the cable to elongate more than 6 millimeters. So we don't want like the elongation in the cable to exceed 6 millimeters. So remember, there are two conditions. First, stress, and then second, elongation. All right, because we know if the load is too large, it may cause excessive stress in this cable and it tear down, or maybe the elongation is too big that the whole thing's deform and something that we don't want. So how we approach this problem? Always you should start with free body diagrams so you could understand how the forces are reacting. So A is a pin, and we know for pin or joint always there is two reactions, one in X and one in Y direction. So let's call them AX and AY. Let's start with taking a moment about point A so we can find basically the tension in the cable. So take the moment about point A equal to 0. The reason we take the moment about point A because we don't need AX and AY. Why don't we take the moment about point A so we could get rid of AX and AY? So for me to take the moment about point A, I look at load P. Load P, try to rotate it counterclockwise, so it is positive. So P multiplied by the distance, which is 3.5 meters. What about this load T? Well, it's difficult to find the perpendicular distance between the line of action and point A. As we explained before, in this case, we'd better break down the load to its component. Let's do so. If I break it down to, let's say, X and Y component, let's call this direction Y and this direction X. Then simply, if I break it down to X and Y, it's gonna be, let's say, always I draw the horizontal and parallel lines so I don't make a mistake. So I would have then two components, one in X and one is Y direction. And let's say if this angle is alpha, let's call this angle alpha. Then this angle has to be alpha. So it means now this load is T cosine alpha, and this one I just write it down here is going to be T sine alpha. So do we have alpha? Yes. In this triangle, if I write down below here, if I write down tangent alpha equal to, I'm gonna have 6 divided by 4, and from here I can find alpha, which is 56.3 degree. All right. So if I continue with taking moment, this T sine alpha is passing through point A, so there is no moment, but this T cosine alpha try to rotate everything clockwise, so it's going to be minus then T cosine alpha multiplied by the distance, which the distance here is 6 meters, equal to 0. So from this one we could find T, which is equal to 10.5 P. Remember, we haven't yet found basically a number for T or P, but we found a relation between T and P. In other words, we found that when you apply load P, whatever load, how much tension the cable is going to experience. So that's the relation. All right. Now we try to calculate the stress and deformation. Let's start with the stress in the cable. So stress in the cable. Stress definition is force divided by area. The force is T divided by area, right? And force here is 1.05 P divided by the area. Area is the diameter of the cable is 4. So it's going to be then 4 pi, right? So this stress, we know it has to be less than 180 megapascal, right? The question says it has to be less than 180 megapascal. So from this one, I can find P, which has to be less than 2154 Newton. All right. So that's so far one relation that we found. We found that the force has to be less than this number. We just calculate this value over here, right? In order to, for us, that cable has a stress less than 180 megapascal. But we have also another condition. We have the elongation condition, which shouldn't exceed 6 millimeters. Let's go for the elongation in the cable. Let's calculate that. So elongation in the cable. And the elongation formula is delta. We have a formula FLAE. Let's substitute these numbers. Force again for us is 1.05 P. The length of the cable, we can calculate it from this triangle, right? It is 4 meters here, it is 6 meters here. So this length then becomes, if I use Pythagoras formula, 2 square root of 13. But be careful about the units. We want everything in millimeters. So I multiply it by 1000. All right. Area again for the cable 4P, and modulo of elasticity to 10 to power of 5 megapascal. Be careful. This unit is in megapascal, right? Original value that we have is in gigapascal. As I said during the lecture, be careful about unit here. So this is a total elongation, and we want the elongation to be less than 6 millimeters. So if I solve this equation, I would get P has to be less than 1991 Newton. All right, that's our second condition. So by checking stress, we found P to be less than this number. By checking elongation, we found P has to be less than this number. And we know that we have to meet both of these conditions. So if I pick the first number, then it means I'm not going to satisfy the second condition. So from here, in order to satisfy both conditions, we from, let's say, equation 1 and equation 2, we can 1 and 2, we can make the conclusion that the maximum load that we can apply is 1991 Newton, or it has to be slightly less than these numbers, right? Because we want to satisfy both conditions. Let's say if you apply 1990 Newton, like 1 Newton less, you're satisfying condition 2 and you're satisfying condition 1, meaning that the stress in the cable is going to be less than this allowable stress, and also elongation is going to be less than 6 millimeters. Well, in problem 3, we have a cube, which is, the question says it's under pressure from the y and z direction, right? So pressure in y direction. And remember, always when we say pressure, it is from one side and also from the opposite side, because everything has to be balanced. And in z direction as well. And so that's the pressure. So when we say pressure, remember it is a stress basically. So what we say is sigma y and sigma z, they are minus 5 megapascal, right? Pressure and stress, they have the same units. Remember, it says it's pressure and it's 5 megapascal. But it says that we have also a tension, basically, a tension in x direction, right? It's a force, and this force is 4 kilonewton. So, but simply I can calculate stress in x direction. First of all, it's positive, and it is force divided by area, right? So it is 4,000, let's convert it to Newton, divided by the area, which the area that this force applies is 10 multiplied by 40. If I simplify it, it's going to give me 10 megapascal. And it is positive, remember, it is a tension. So again, pay attention, for y and z, we didn't have to divide it by the area because it's already pressure, it's a distributed load. But here we have a force, we divide it by area. So we want to know how much this cube or this box is changing in x, y, and z direction. In other words, we want strain in x, y, and z. And we know that we have a formula for epsilon x, epsilon y, and epsilon z, which is basically the Hooke law. So for example, for epsilon x, 1 over e sigma x minus nu sigma y plus sigma z, right? And if I substitute this number 1 over e, so we have the value for e 2 10 to power of 5. Sigma x is 10 minus Poisson ratio 0.2. Don't forget the sign for sigma y and sigma z. They are minus 5 and minus 5. So these signs, they are important. So we can do the same for epsilon y and epsilon z. I let you guys to continue that. So if we have epsilon, these are a strain, right? Remember, these are strain. But the question asks us to find deformation. Deformation. So let's see what's the difference between deformation and strain. If you recall, we define a strain as delta deformation divided by L, right? So which this L is the initial length. So it means if I want deformation, I have to multiply epsilon by L, right? Always when you want deformation, the actual deformation, you need to multiply it by the initial length. And this is from the definition of the strain. So if that's the case, then the rest is easy. If I know epsilon x, epsilon y, and epsilon z, it means delta x is going to be epsilon x multiplied by its original length. In x, the original length was 8 centimeters or 80 millimeters. Similarly, for y direction, it's going to be epsilon y multiplied by 10. And in z direction, the same is going to be epsilon z multiplied by 40 millimeters. So these are the deformation in x, y, and sorry, I need to correct this one. This is delta z. All right. So these are the deformation in x, y, and z. Now, let's see, if you have a cube, it's under stress like that. Now we know how much in x, y, and z this box is changing. So it means we can calculate how much the volume of this thing has changed, right? If we know the new size, because we know how much delta x, delta y, and delta z are. It means we can find out how much the volume of this box has changed, which is the topic of the next problem. Well, let's see how we can solve this problem. We want to know how much the volume of these cube chains, this cube, the size is A, B, and C in X, Y, and Z direction. And it says that it is under stress in all directions. And remember, we don't know the sign of these. Like, we just want to solve a general case. We don't know if they are tension or compression, if they are pressure or tensile load. So let's for now assume they are all positive. So I have then stress in all direction in X, Y, and Z. All right, and let's call them, like, this one is sigma X, this one is sigma Z, and this one is sigma Y. So we know because of this stress, this box is the size in each direction is going to change, right? So for example, in previous problem you saw that we calculate delta X, how much the size in X changing, or in Y and in Z. Let's write it down. Volume when there is no force is A, B, and C, right? ABC. We have the size, so the initial volume is ABC. The volume after we applied load, let's call it V1. V1 is then A plus delta X, B plus delta Y, and C plus delta Z, right? I just assume that the deformation in X, Y, and Z, they are delta X, delta Y, and delta Z. I don't know the numbers, I don't know the sign, I just assume they are like some values. So if I simplify this relation by just factoring A from the first bracket here, I get 1 over delta X divided by A. I factor B from the second bracket, then it gives me that number, and C from the second bracket, the third bracket, sorry, delta Z over C. So if I simplify this one, and also if I pay attention for these delta X, delta Y, and delta Z divided by A, B, and C, that's in fact definition of strain. Remember, the key formula, strain epsilon, was delta divided by the initial length. All right, so then it's going to be simplified ABC 1 plus epsilon X 1 plus epsilon Y and 1 plus epsilon Z. Right? So far let's see what we did. We have the definition for epsilon. We substitute these values, right? And we calculate volume 1. Now let's see if we can simplify this relation one more step. So then I would say is equal to A, B, C, and it gives me 1 plus, I'm just multiplying this guy, this is going to be epsilon X, epsilon Y, epsilon Z, plus epsilon X, epsilon Y, epsilon Z, epsilon X, epsilon Y, epsilon X, epsilon Z, and epsilon Y, epsilon Z. You can try it later to make sure that I didn't make a mistake. All right, so I just multiplied these 3 brackets and I got these things. Ugly formula. So we know epsilon X, epsilon Y, and epsilon Z, they are small numbers. Now if we multiply 3 small numbers together, we get a very, very small number. For example, if, let's say, for just sake of the discussion, if epsilon x is 0.1, epsilon y is 0.1, and epsilon z is 0.1. Then what do we get for this one? We get a very, very small number, right? And similarly, we get a very small number for this guy. So with this logic, it's fair to say that we can ignore these values, right? So we can say that this value is a small, 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 and we can ignore them. So it means my relation here becomes a, b, c, 1 plus epsilon x plus epsilon y plus epsilon z. So we were looking for finding delta v. Delta v is v1 minus v0, right? We found v1, we know v0. If we do the calculation, we get a, b, c, epsilon x, epsilon y, and epsilon z. We know that this basically ABC is V0, so I can then simplify the whole things by writing delta V over V0 is epsilon x, epsilon y, and epsilon z. And this is a formula which you can use, so you don't need to basically know the proof, but in other problems you can simply use this formula, which next problem you will see how we can use this formula. All right, even we can go one step further and substitute this epsilon x, epsilon y, and epsilon z by sigma x, sigma y, and sigma z. How we can do that? It's from Hooke law. We know, so I write it down over here. So from general Hooke law, we know epsilon x is equal to 1 over e sigma x minus nu sigma y plus sigma z. And similarly, we have a formula for epsilon y and epsilon z, right? If we substitute this epsilon x, epsilon y, and epsilon z there, so if I substitute then this epsilon x, epsilon y, and epsilon z in this formula, then I would get delta v over v0 equal to, and let's say we simplify it, we will get 1 minus 2 multiplied by nu divided by e sigma x, sigma y, and sigma z. And it is a nice formula which later you guys can use when we want to calculate the change in a volume. So I encourage you guys to substitute this epsilon x, epsilon y, and epsilon z here, and make sure that I haven't made a mistake, and you get the same basically formula for delta v over v0. So now that we know this formula, let's move to the second problem. Well, this problem, we want to find the change in a volume of a cube, which the cube has like the size, it's 1 meter by 1 meter and 1 meter. It's a large cube. We throw it down to the sea, and it is underwater, and because of that it is under pressure, right? So from all the side, and we know underwater the pressure is uniform from all the side. So if it is under pressure, then simply I know sigma x is equal to sigma y is equal to sigma z, and it is equal to the pressure underwater, right? So pressure under water, which from physics we learned that the pressure underwater, so don't forget that we also need a negative sign here because it is pressure, minus rho gh. So we just Google and look up the for the C, basically the density, which is 1024. So that's the density, and the unit, if we check, it is kilogram per meter cube. G 9.81, and the question says we put it 2 kilometers, right? 2 kilometers below the water, so basically 2000 meter. So I have then sigma x, sigma y, and sigma z. Now if I want delta v divided by v0, it is simply the formula that we just proved, and we said we can use it, 1 over 2 nu divided by e, sigma x, sigma y, and sigma z, right? And we have all the numbers that we need here. The volume is 1 meter by 1 by 1. We have value for E. Don't forget it is in megapascal. You need to convert it to Pascal, so which is 10 to power of 11 Pascal. And we have the value for nu, which is 0.25. And we just found the value for sigma x, sigma y, and sigma z, which please continue the rest. And you should get a negative number because it is under pressure. Well, problem 6 is a very simple problem. We have a plate. It's a thin plate. The thickness is 2 millimeters. And so we call something a thin plate when the size of the other size compared with the thickness are large, which here we have like 10 centimeter by 20 centimeters. It is under some loads stretching from x and y direction, and we want to find out stress and strain in all three directions, right? So very simple, we start with stress. So sigma x is so the formula force divided by A, the area, right? So what is the force in x direction? Let's say in x direction the force is 1000 Newton, and it is a positive because it's tension, right? It's a positive load, and multiply by the area, which is 100 multiplied by 2. Remember, the area that we need to consider is like this area, right? So from here I can find it. It's gonna be 5, and based on the unit that I choose, it's 5 megapascal. Similar for sigma y. Sigma y is gonna be F over A, which we don't have any force here. It's going to be then 0, nothing in y direction. And sigma z is going to be similarly F over A, which what is the force is 2 kilonewton, so 2000, and again it's positive, and the area is 200 millimeters multiplied by 2, which gives me 5 megapascal. Similar to sigma x, the load was larger, but the area also is bigger. We got the same number. And the next step, we want epsilon x, epsilon y, and epsilon z. We have the Hooke law, 1 over e sigma x minus nu sigma y plus sigma z. So what about sigma y, epsilon y? So one mistake that the students I've seen a lot do is when they see sigma y is 0, they immediately make a conclusion that, well, if that's the case, then it's safe for me to say epsilon y is equal to 0, right? Because if we don't have any stress, then we shouldn't have any strain. Is that correct? I want you to pause and think about it, and you can intuitively think about it that when you have like loading x and y, you are stretching these basically plate, so you expect that it becomes thinner, right? So there must be some change, but we don't have any stress, right? So if you come back, probably you guess that this is wrong. What we do, we just follow Hooke law. We trust Hooke and his formula, and we let the math to find out the value for epsilon y. And this is a formula for epsilon z, which is sigma z minus nu sigma x plus sigma y. So remember, we just substitute these numbers. I then ask you guys to do it on your own, and you should get these values for strain. 210 to power of minus 5. So these are very, very small numbers, but please pay attention that this is a positive values. This is a positive values as we expected, right? Because in x and in y direction we are stretching this plate, but in y we got a negative numbers, which makes sense, and it is half of epsilon x and epsilon y. Problem 7 is an interesting problem. We have a plate and it is under a stretch in x and y direction, and we want to know how much the diameter is changing, right? So probably you can guess it involves some geometry. If we apply some stretch in x and y direction, then the size in x and y is going to change. Now we are interested finding out how much the diameter changed, right? This diameter, sorry, not the diameter, the diagonal AC. So simply we can say that, let's exaggerate and say because of this load, this length DC increase by this amount, and this AC is increasing by this amount, and we want to find out like this new diameter. Let's call this one A prime, and let's call this point C prime, right? So our objective is finding these A prime, C prime, the new diagonal of this plate. And again, I exaggerated, it's not going to be that large. Well, we already know that because of these stresses, how much is epsilon x and how much is epsilon y. We can use Hooke law for a 2D problem. So 1 over E sigma x minus nu sigma y. So remember, this is the Hooke law for 2D problem. You may say, well, why it is a 2D problem? Because the question didn't show or didn't say anything about the third dimension, the thickness of this plate. So we can assume that it is a 2D problem. Or even if you use a 3D formula for Hooke law, you would get the same result, because anyway you're going to put sigma z equal to 0, right? Sigma x. So we have all the value for sigma x, sigma y, nu. question gave us all this information, so we can find epsilon x and epsilon y. If I know the strain in x and y direction, then simply CC prime is gonna be epsilon x multiplied by the initial length DC, which is gonna be then epsilon x multiplied by 30 millimeters. And similarly, A prime is gonna be epsilon y multiplied by AD, which is epsilon y multiplied by, again, 30 millimeters, right? So don't forget, we always use the definition epsilon equal to delta over L, right? So if I want deformation, delta is strain multiplied by the length. And this is in fact what we did here, right? This is what we did. We said the CC prime is strain multiplied by the initial length. Similarly, AA prime the same. So as you can see, the rest is just easy, and you can find CC prime, AA prime, and if you know CC prime, then the rest is geometry, which I let you guys to figure it out. Well, problem 8, it's a common problem in civil engineering, sort of when we deal with building structures. It's very common to use concrete and steel together. And again, this is a very important problem which you need to understand it. So we have a combination of concrete and steel bars. And as you can see, these two materials, they are different. Concrete has different value for like its module of elasticity, and steel the same. We have its module of elasticity, which is a different number, way larger than concrete. Concrete is a brittle material, it breaks easily. Steel is a flexible material, but these two combined together makes a perfect, strong, basically material for a building. If somebody use them alone, like concrete by itself or steel by itself, you may not get the result that you desire when compared with when you combine these two. Let's solve this simple problem as an example, so then later you know how to deal with this sort of problem. So we have a column or a post made out of concrete, the outside, and we put 6 basically a steel bar inside that. And remember, we assume in this sort of problem that these two bound together, they are not gonna separate. So we apply load 1500 kilonewton. So this is the total load, which is a very large load, or 1510 to power of 5 Newton. So I convert it to Newton before I forget about the unit that it is in kilonewton. So we know out of like this load, some of this load goes to concrete, some goes to steel, right? So we know then this 15 10 to power of 5, it's some of it goes to a steel, let's call it PS, and some of it goes to concrete, right? But we don't know the portion that goes to a steel and the portion that goes to concrete. But something that we know, when we apply that this load, the whole thing is going to shrink down, it's going to become smaller. But we know that since steel and concrete, they bound together, the amount that the concrete shrinks is equal to the amount that steel bars shrinking. In other words, we know that delta steel is equal to delta concrete, right? It's common sense. Otherwise, if let's say concrete shrink more than steel, it means these steel bars are going to stick out and the whole thing is going to break, right? Because they separate, but we don't want that scenario. So we have a formula for deformation. And so I write it down here. If you forget, the formation delta is FLAE. So based on that concept, then this is PS, and the length is L. Let's call this one L for now. AS and ES, and this one is P concrete, L, AC, E concrete, right? So let's see if we have the information. We can get rid of this L. ES and EC, question gave those information to us. What about AS and AC? That's easy, we can easily find out. Let's say, I'm just gonna exaggerate it. Let's say this is the concrete, and let's say this these are the basically the steel bars that we have, and we have 6 of them. 1, 2, 3, 4, and let's say this is the 5th one and this is the 6th one. They are not equal, but you can accept that. From here I can say that the area of a steel, I have 6 of these, multiply by pi, and the radius of each of them is it says 20 millimeters, so then the radius is 10 millimeters, 10 to the power of 2. It gives me 600 pi. What about concrete? So concrete, the whole diameter, so pi multiply by 225 square minus 600 pi, right? Whatever number it gets. So remember, the area for concrete is the whole things minus these 6 holes, which is basically a steel. So let's see what we got from equation 1 and equation 2. 1 and 2, we can find PS and P concrete, which again I left it here and I let you guys to solve it. It's very simple. To unknown 2 equations, and after you have the force, then you can easily find stress in a steel, which is a force in a steel divided by area of a steel, and stress in concrete is force in concrete divided by A concrete. Well, let's deal with the last problem. That's one of the most important problems in module 2. Again, another classic problem. You need to know how to solve these sort of problems. So I'm just going to give you some hint here and let you guys to solve the rest of problem. Let's say let's start with finding out how this mechanism or this structure works. We have this BDE, this horizontal bracket, which the question told us it is rigid, right? So it is rigid in a sense that maybe compared with the rest of the structure, it's so strong that it doesn't deform. And we have 2 links, AB and CD, these 2 links, and apparently these 2 links, they are deformable, they are flexible. One of them is made out of aluminum, this AB is made out of aluminum, and the other one made out of steel apparently. And we have the information, all the information we need. Also remember, the cross-section area is different. Apparently CD is a little bit, I guess, larger. Yeah, link CD has a cross-section area of 600 millimeters. So let's see how everything is gonna then react or deform in this problem. So I apply 2 kilonewton load at the point E here. So when I apply load here, you can imagine this, the whole things here, this BDE likes to sort of deform, and not deform, to rotate, right? About maybe point B. But this links doesn't let it to happen. So like always, we start with a free body diagram. We say, well, these links, they have a job. They apply load, which we don't know their direction. For now, we just assume it's positive. And let's call them for now F1 and F2. Like this one, we call it F1, and this one, we call it F2. And we know that because we are in a static, everything has to be in equilibrium. Using the equilibrium equation, we know that sum of the load in y direction must be 0. So then F1 plus F2 must be equal to 20, right? And what else? We know that nothing has to rotate, so take the moment about any point. Let's take the moment about point B, must be 0. So with that, F2 multiplied by the distance, which is 0.4, and it's try to rotate it counterclockwise, so it's positive 20 multiplied by total length, which is 1 meter, equal to 0. So from here I can find F2, which is 50 kilonewton, and from equation 1 I can find F1, which is minus 30 kilonewton, right? So if I find F1 to be negative, so it's a sign that the load in AB is a compressive load, which makes sense. When you apply this load here, probably this link CD is under tension and this AB is under compression. So if AB is under compression, it means its length is going to decrease, right? It's going to become basically a smaller. Let's say this point B deform and goes there. And let's say this point D deforms and maybe comes down here. Let's call them this one B prime and this one D prime. All right. So in other words, if let's say this is a line from passing through BDE, now this link BDE is going to deform to something like this. And again, I'm exaggerating, it's not going to be that much, right? And then this one is going to be point E prime over here. So let me complete this one, right? So this line then is all the way coming down here, and this is E prime. Our job is finding these E prime. This is what question asks us. All right, so let's see what information we have. Do we know how much this deform or how much this BB prime is? Yes, we do, because we know BB prime is equal to FLAE, F1, L1, A1, and E1. For simplicity, I just call this one link 1 and I call this one link 2, right? And similarly, I can find out D prime, which is F2, L2, A2 and E2. We have all the information that we need, so easily I can find out BB prime and DD prime. Now the question is how to find EE prime. So I'm gonna let you guys to find it. It's just geometry, it has nothing to do with this course, but I'm gonna give you a hint. So probably you forgot, you've either read it in high school or maybe in one of your math course. Google Thales, or some people call it Thales. Taylor's theorem. And based on that, which is a geometrical theorem, it gives you the relation between these in a triangle. It gives you the information between these EE prime, DD prime. So another hint, call this point maybe like this point. Call it O and try to figure out how you can use this Taylor's theorem and find out this EE prime. Let me write it better so you don't get confused. This is not a K. This is Taylor's theorem. Alright guys, that's it. Please review this problem, and if you couldn't follow any solution, as I said at the beginning, send me an email and we can go over each part that you don't understand. Good luck.